Hello guys, I am MD Mohammed Hussain and welcome to my channel Math and Reality. Today I will tell you about an interesting thing in number theory, that is divisibility. So first learning about divisibility, I want to talk about some basic things about or I should say basic operations of numbers, that is addition, subtraction, multiplication and division. So if we talk about especially integers, we know that if we add two integers we can get integer, subtract two integers we can get integer, and multiply two integers we also get integer. If we divide an integer by another, can we get integer all the time? The answer is no. It is not necessary that if we divide an integer by another, we get an integer. It is not necessary. So we can by this division criteria that we do not always get integer, although we dividing an integer by an integer. So why is that? And we can learn about it from the rule of divisibility. That is, I will discuss about in this channel and now. So, what is divisibility? So, if we say that m comma n are integers, I am assuming those two as integers. You can also assume those as positive integers. I don't care. So m and n are integers. So if we say that n is divisible by m, then we can write like this. Or we can write like this, where k is an integer. Okay, so we read this like n is divisible by m, and it is a divisibility sign. Okay, and we can say that m is a multiple of n. Okay, m is a multiple of n. Okay, so it is some this is some basic introduction of what divisibility is. So we can get into some proofs. Okay, we can get into some proofs and some problems. Then you can very much understand that what I am talking about. Okay, so we have some rules, but first I have to show you a rule that if n is an integer, and absolutely n is an integer but not, I am meaning to say that we divide an integer by another, but that another integer has to be an integer except 0, because if we divide a number with 0, that's making no sense. So we all know that we can divide if this relation is always true. This relation where n is integer except 0. Because if it is 0, 0 by 0, that making no sense. So this relation is always true for real numbers or complex numbers, for all numbers. Okay? So we can go to some propositions. And first proposition is x is divisible by x. Reflexibility, we call it. If we have a number except 0 and we divide it by itself, we can get an integer. And this proposition is as the same thing. Okay, if we divide an integer by its own, we can get an integer, and it is always true. We know that if we divide 1 by 1 or we divide 3 by 3, we can get an integer. It is 3 is always divisible by 3. 1 is divisible by always 1. And 100 and 1 million is divisible by 1 million. And I am trying to say that an integer is always divisible by itself. That is easy and clear. So this is my first proposition, and I am moving to second one. Second proposition is saying that if z is divisible by x and z is divisible by y, then I made a mistake. If y is divisible by x and z is divisible by y, then z is divisible by x. We call this proposition is transitivity. Okay, transitivity. Okay, this proposition name is transitivity. Okay. Transitivity. Okay. So we can prove that very easily. We know that y is divisible by x. Then we can write it by our divisibility definition, kx, where k is an integer. So, and also we can write z equal to k1y, but we can put this value into this, then we can get k1 kx. But look, z is a multiple of x. Then we can write z is divisible by x, and we proved it, right? From the definition of divisibility, we can write that y is a multiple of x, and where k is an integer. Then we also, from this, we can write z is a multiple of y. Then we can put the value in here, and we get that z is a multiple of x. Then we can write like this. Okay. So for the third proposition, we have if y is divisible by x and y is not equal to 0, then modulus of x is less equal than modulus of y. It is the third proposition. So we have a proof of this. So if y is divisible by x, so we can write that y is a multiple of x, right? So we assume that modulus of x is greater equal than 1. It is true because k is an integer. We know that. So if we take modulus on both sides, we can get this, right? And for the inequality, replacing this by this, we can get 1 into modulus of x, which is this. So if we take the inequality, we can get modulus of y is greater equal than modulus of x, or we can say that the modulus of x is less equal than modulus of y, and that is proved. Okay, we know that k is an integer, so if we take the modulus, it will be strictly positive. Am I right? So it will be strictly greater equal than 1, right? So we can write it by like this with the help with the use of inequalities. Okay, so we go to the fourth proposition. So fourth proposition is, if y is divisible by x and z is divisible by x, then x divides alpha y plus beta z for any integers alpha comma beta. This proposition is simply telling that if y is divisible by x and z is divisible by x, then x will divide any linear combination made by y and z. Okay, I think you can understand. So we have to prove this. So what is the proof? So we know that y equal to kx, we can write it because y is divisible by x and k is an integer. Okay, so also, so this and okay, then also we can let that z equal to k1x, where k1 is an integer. So alpha y plus beta z, we can put this value in this alpha kx plus beta k1x, and we can common this x plus beta k1 into x. So from this we can see that this thing is a multiple of x. This thing is a multiple of x. So we can write that x is this thing is divisible by x. Right? So this completes the proof. So to the proposition number 5, these are the basic rules of divisibility, and they are easy to prove. You can prove yourself. But what is the main thing in this, that you have to understand the meaning. and the criteria that how divisibility works, right? So to the 5, so if y is divisible by x and y plus minus z also is divisible by x, then z is divisible by x. Okay, so we are going to prove directly. So we can write y equal to kx, where k is an int, right? So also we can write that equal to, sorry, z equal to q1. Am I right? From this thing we can write this. So if we put this in here, we can get kx plus minus z k1x, and turning this here, we can get but look at this. It is a multiple of x. Z is a multiple of x. It is important to see that. We ignore this plus minus. We have to observe that the z is a multiple of x. We can express it like a multiple of x. So we can write that z is divisible by x. And this proof is completed. Okay? So to the sixth proposition, if y is divisible by x and x is divisible by y, then modulus of x equal to modulus of. So let's get into the proof. So we know that from proposition 3 that if y is divisible by x, we know that modulus of x is less equal than modulus of y. And we know. Then from the same definition, we can say that when x is divisible by y, we can write that modulus of y is less equal than modulus of x. But you can see from inequality that if two numbers are less equal and great equal at the same time, less equal and great equal from each other, what does that mean? This means that they are equal. It is a very straightforward thing in inequality. You can check it if you like. So we have completed our proof. Okay, it was a very straightforward proof, and you could check it if you like that this thing is true. So to the proposition number 7. And it is a very, very important proposition. Very, very important proposition, and I will solve a problem using this proposition only. And a very tricky problem, but it will simplify very easily. You wait and see. So this proposition is if y is divisible by x, and y is not equal to 0, then y by x, then y is divisible by y by x. Okay, so let's jump into the proof. So we know that y equal to kx from the definition of divisibility, right? So then we know that can we write? Of course we can write, because y is a multiple of k. Am I right? So from the definition of divisibility we can write this. But we know that from this that y by x is equal to k. So we have to put this in here. Y by x equal to y. And this completes the proof. Okay? It was also a straightforward one. Okay. So to the eighth problem, then I will talk about a little. Then I will jump into some problems. So the last proposition is, for z is not equal to 0, if y is divisible by x, if and only if if and only if xz is divisible by what? Okay. So let's get into the proof. So from this definition we can write y equal to kx, where k is an integer. So we could talk about something. If this is true, and we know that z is not equal to 0, then we can multiply both sides by 0. Because z is not equal to 0. So if we multiply both sides by z, and we can bracket this to show that xz is a divisor of yz. Or we can say that yz is a multiple of xz, right? So then we can write like this, and it completed the proof. It was also a straightforward proof. So, and I was talking about that I will talk a little, but why? Or what I will talk about a little. That is the number 7 proposition, and you will see that the end of the discussion it is playing a very important role solving some problems. So what was the 7th proposition? That if y is divisible by x, and y is not equal to 0, then y by x is a multiple of y, right? So what is the significance about this proposition? So the significance of this proposition is if we assume that, or if you observe that, until a perfect square, every number has every positive integer has an even number of divisors. Okay, if we observe that until a perfect square comes on our way of counting. Every positive integer has an even number of divisors. Okay, so this idea tells also something else, that all the positive divisors, okay, of all the positive divisors of a perfect square, appear in pairs. Okay, appear in pairs like this. If one is x, other will be y by x. Okay. All if all positive integers divisors are even until it is a perfect square, then a perfect square's divisors will appear in pairs like these. Okay, and we can call, if appear in pairs the divisors, then we can call that number a perfect square. So we can identify perfect squares using this theory, right? So we can write that n equal to m square, where n and m are integers, and this condition is called perfect square condition. Okay, that n is a perfect square. N is equal to a perfect square, or n is a perfect square. We can say that. So if n is not a perfect square, we can write it like this. And we can call it like n is a square-free number. Okay. If n is equal to n cube, where n and m are integer, then we can say that n is a perfect cube. Or else we can say, if n is not equal to n cube, then we can say that n is not a perfect cube. Or we can say that cube. Or if s is greater equal than 2 and n equal to n to the power s, then we can call it that n is a perfect power. We can call it n as perfect power. Okay, so these are some informations about perfect squares, perfect cube, and perfect powers. This will come handy when I will jump into some other number theory problems in the future. So first problem we have to deal with. I said that earlier that we will deal with it using proposition 7. Okay, so let's write it. 20 bored students take turns take turns walking down a hall, walking down a hall that contains a row of closed lockers numbered numbered 1 to 20. The first student opens all the lockers. The second student closes all the lockers. Closes all the lockers numbered 2, 4, 6, ... 20. But this is meaning that he closes all the even numbered lockers. Okay. So then the third student operates on the lockers numbered 3, 6, 9, 12, ... 12, 15, 18. Okay. If a locker was closed, he opens it. And if a locker is open, he closed it. And so on. For the ith student, he works on the lockers numbered by multiples of I. Okay. If a locker if a locker was closed, if a locker was closed, he opens it, he opens it, he opens it, and if a locker is open, he closes it. What is the number? What is the number? What is the number of the lockers that remain open after all the students finish their works. Finish their works. Okay, so it is a very big question, but I will try my best to make you understand it. Okay, but first of all, I give you a hint that you should use the proposition 7 that I proved earlier, and you can pause the video and try this problem by yourself first, then watch my solution. Okay, so we are ready. So it is said that 20 board students take turns walking down a hall that contains a row of closed lockers. Okay, so numbered 1 to 20. Okay, the first student opens all the lockers. Okay, the first student opens 1 to 20 all the lockers. The second student closes all the lockers numbered 2, 4, 6 till 20. Or we can say that the even numbered lockers, or we can say that those numbers that are divisible by 2 or a multiple of 2. Okay, that numbered locker the second student opens. So the third student operates on the lockers numbered 3, 6, 9, 12, 15, 18. Or we can say that the multiple of 3s. Okay. If a locker was closed, the third student does if a locker was closed, he opens it. And if a locker is open, he closes it. And so on. For the ith student, he works on the lockers numbered by multiples of I. Numbered by multiples of I. He operates the locker whom are multiples of I. If a locker was closed, he opens it. And if a locker is open, he closes it. So what is the number of the lockers that remain open after all the students finish their works? So the operation students does on a particular numbers multiples, right? So we can use the proposition 7. And how will we use this? Let's see. So we can start with the solution. So that that ith locker is operated by jth student. Ith locker is operated by jth student. So we know that ith student will operate. Ith locker is operated by jth student if and only if j is divisible by I, or I is a multiple of j. We know from the question. So I, right, but from proposition Proposition 7, we know that if j is divisible by I, then I by j is divisible by j. Oh, sorry. J by I is divisible by j. We could say that very easy. So then the remaining the open lockers divisors will be in pairs, right? We know that from proposition 7. So we can write it like j by I comma I. Okay, that pair. But if that is true, then the remaining open lockers will be the perfect squares between 1 and 20, right? And by the proposition 7, right? So what are they? We know that between 1 and 20, the perfect squares are 1, 4, 9, and 16. These 4. So, if they represent the number of lockers that remain open after all the students finish their works, so then the answer will be 4. And it is our answer. Okay? So by using proposition 7, this problem become a piece of cake and a very, very short problem. The question was very big, but its solution is very short. Am I right? So that's why I was talking that if we learn divisibility rules, we can solve very hard number theoretic problems in a jiffy. Okay, so let's go to the next problem. So for but before going to the next problem, I have to discuss about something. In integers, we know that there are some integers that are divisible by 2, and some integers that are not divisible by 2. So those who are divisible by 2 are called even integers, and those that are not divisible by 2, they are called odd integers. Okay, so there are some operations. I will not write on the board about it because they are very straightforward. You can check yourself, but I will little talk about it, then we will jump into the problems. So if so the first thing is the even number is formed like this, 2n, where n is an integer, and our odd number is like formed this, where n is an integer. Every even number is the form of this, and every odd number is like the form of this. Okay, then if we add two even numbers, we can get an even number. If we subtract two even numbers, we can get an even number. Okay, so if we multiply two even numbers, we can get an even number. Okay, if we add two odd numbers, we can get an even number. If we subtract two odd numbers, we can get an even number. But there is a restriction that if two odd numbers are same, we will get a 0. So that's not counted. Okay, the two odd numbers has to be distinct. So also that goes for even numbers as well. So then the multiplication of two odd numbers are always odd, and if an even number and an odd number is multiplied, then we can get an even number. Okay. Also if we add odd numbers even times, okay, if we add odd numbers even times, then we can get an even number. If we add odd numbers odd times, then we can get an odd number. Okay, and if we multiple some integers, except 0, it will be even if and only if among the divisors of the multiplied property, at least one is even. Okay, we can think like that. Here A1, A2, A3, till AN. Okay. So this product will be even if at least one of them is even. Okay, this product will be even if one of the A's are even. Okay, so these were some properties that I was talking about. So let's jump into the problem. First problem is 2 to the power n is the sum of where n is greater than 1, it is also 2 consecutive odd integers. ठीक है. So let's jump into the proof. So we have to transform this to the sum of two consecutive odd integers. Okay. So we can write that 2 to the power n equal to 2k minus 1 plus 2k plus 1. These are consecutive odd integers. We can see that. So what is the value of k? So k is equal to 2 to the power n minus 2. Then we can put it here, right? If we put this here, and that is the end of the proof. We transform 2 to the power n as the sum of two consecutive odd integers. You can check that these two are odd, because if we subtract a 1 from a power of 2, we will get an odd integer without any doubt. If we add a 1, we will also get an odd integer. Okay. So then next problem says that 3 to the power n is the sum of 3 consecutive integers. Okay, so there is not very necessity that the integers is odd or even. We have to show that it can be written as the sum of 3 consecutive integers only. Okay, so let's jump into the proof. So 3 to the power n. So we, as the question says, we can say s minus 1 plus s plus s plus 1. Right? So what will be the value of s? S will be equal to 3 to the power n minus 1. Then we can write it like 3 to the power n. 3 to the power n minus 1 plus 3 to the power minus 1 plus 3 to the power n minus 1 plus 1. And these three are consecutive integers. You can check by putting these numbers one by one and check that these are always consecutive integers. Okay, so we completed the proof that 3 to the power n is the sum of 3 consecutive integers. Okay, so and now we will prove a very interesting problem, and I will write it. Okay, that let k be an even number. Okay, k be an even number, and is it possible to write one as the sum of the sum of the reciprocals of k odd integers. Okay. So we have to prove this. It says that let k be an even number. So it is an even integer. So is it possible to write 1 as sum of the reciprocals of k odd integers? Okay. So I will not destroy the excitement, destroy the surprise. So let's jump into the problem and then see what is the answer of this question. Okay. So we will assume that it is true. Okay, we will assume that it is true. Then okay. So if we take LCM of the denominator, we can get n1 till nk equals to s1 plus s2 plus till sk. Okay. So s1, s2, sk are s1, s2, sk are representing the leftovers. So we doing the LCM and taking on numerator. Okay. So we are seeing that this product is odd because these all integer n1 till nk, these all integers are odd, and we know that if multiply odd integers at any times, even or odd, we will get a odd integer, right? And we also know that if we sum s1, s2, sk are all odd integers because n1, n2, n3 are all odd integers, and the product of the s1, s2, sk are also the product of n's specifically. So the sum of the odd integers even times, because k is an even number. So sum of the odd terms even times is an even number. We know that from the rules of even and odd numbers. So this side will be even and this side will be odd. But an odd number can equal to an even number. It is impossible. So we reach a contradiction. Okay, because an even number and an odd number cannot be equal. So we reach a contradiction that it is not true. It is not true. Okay. So, but if we take something like that, this is true. We could calculate this thing, and you will see that 15 plus 1 35 plus 45 plus 2, sorry, 1 by 231. This sum is equal to 1. Okay, this sum is equal to 1. But the previous one we proved it is not possible. It is not possible. Okay, the previous one is not possible. So we get an answer negative. So the last problem of this video, so I have to write it. So the problem is Zach, and it is from HMMT. Okay, HMMT 2004. This problem I got from, and you can post in the comments that what is HMMT competitions, which country hosts it. Okay, so Zach has chosen 5 numbers from set 1, 2, 3, 4, 5, 6, 7. Okay. If he told Claudia what the product of the chosen numbers was, that would not be enough information for Claudia to figure out whether the sum of the chosen numbers was even or odd. What is the product? What is the product of the chosen numbers? So our question is, Zach has chosen 5 numbers from set 1, 2, 3, 4, 5, 6, 7. Okay. If he told Claudia what the product of the chosen numbers was, that would not be enough information for Claudia to figure out whether the sum of the chosen numbers was even or odd. Okay. So what is the product of the chosen numbers? So we have to find which 5 numbers Zach chosen, and we have to find the products of the 5 numbers. Is that right? No, not at all. First, we observe that Zach has chosen 5 numbers from this set, right? So if we from the permutation and combination, we know that Zach has chosen 5 numbers from this set, but the product of the 5 numbers, the product of chosen 5 numbers will be equal to the product of chosen 2 numbers from this set. Am I right? Unchosen numbers. I am trying to say that Zach has chosen 5 numbers. So he chosen 5 numbers from this set. So he chooses 5 numbers from this set, and the product of the 5 numbers will be equal to the unchosen 2 numbers that are remaining, and the product will be equal to the 5 chosen numbers. Okay. So if we jump into the solution, you will be clear about it. So let's jump in, and who there noted my question, you should go on and try this problem. It is a very interesting problem. Okay. Pause the video and try it by yourself, and then look at my solution. So let's go. So first, the set 1, 2, 3, 4, 5, 6, 7. Okay. So if Zach has chosen 5 numbers, the product of the 5 numbers has to be equal to the product of the 2 unchosen numbers, according to the permutation and combination. Okay. So which two numbers will be unchosen? So we have to find first that which numbers can be produced by multiplying 2 numbers from this set more than one way. Okay, more than one way. Okay, so we have to find numbers that can produced by 2 numbers from this set. Okay, produced by 2 numbers multiplying. Okay, multiplying more than one way. Okay, we can see that clearly that 12 and 6 are 2 only candidates, because if you look at closely and observe these numbers, that 12 can be represented by 3 and 4 from this set, and 2 and 6. Okay. And 6 can be represented 2 and 3 and 1 and 6. And no number can be represented the product of 2 numbers. Product of 2 numbers more than once. Okay, no number can be represented like this. Okay, so we find 2 numbers, so it completes the first case. Okay, it completes the first case. So in second case, it has to be the sum of the it has to be the 2 unchosen number. the sum of the two unchosen number has to be an odd number. How it is? If we take five numbers, if we take five numbers, like we could say, we take all even numbers. Okay, three even numbers, 2, 4, 6. Okay, 2, 4, 6, and we have to take two odd numbers. Okay, so we have to take odd numbers. So if we sum them, there will be odd numbers, right? There will be odd numbers. So we have to take from them, from this criteria, that which two numbers sum is an odd number. Okay, sum is an odd number. The odd number. So you can say that. What about 6? It says the two numbers sum is also odd, but in this case it has to be at least one set, exactly one set. That is what. Okay, it has to be exactly one set. That is what. Not all the sets. That is the sets element sum is odd. Okay, I am trying to say that. Mainly, I am trying to say that these two numbers we found in the first case. In the second case, two unchosen numbers sum has to be an odd number. From learning from this question, okay, sum of the two unchosen number has to be odd. So the five unchosen number also be odd. Okay, the sum of the five unchosen number also be odd. Okay. If that is the case, so from first and second case, the appropriate number will be 12. Okay, from two cases. Okay, from two cases, the appropriate number will be 12. Okay, so the number of the product of five chosen number will be 1 into 2 into 3 into 4 into 5 into 6 into 7 by 12. That will result in 420, and this is our answer. Okay. This problem was very tricky, and we have to think about two cases. So first was that from these numbers, Zach has chosen five numbers. So we have to, if we have to find the product of five chosen numbers from permutation and combination, you can say that the product of five chosen numbers is equal to the product of two unchosen numbers. Okay, two unchosen numbers, and from this we can get these two things. Okay, then from the second case, we know that the two unchosen numbers sum will be odd. So the five unchosen numbers sum will also be odd from the permutation combination thinking. So then from the second case, From the second case, we knew that 12 will be an appropriate number. 12 will be the appropriate number. Okay, 12 will be appropriate to divide the whole product and get the product of the 5 chosen numbers. Okay, so this is our answer, 420. Okay, so that's it all, guys. I hope you like my video, and if you like my video, please like and subscribe and recommend me if you like, and please encourage me to make videos like those in the coming future, and keep learning about new things about mathematics, because if you jump into mathematics, you can see that there are very, very beautiful patterns and many beautiful things in it. Okay, so that's it for today. Thank you for staying with me, and goodbye.